Hello everyone, this is Amir from Audio Science Review. I have a technical topic for you that's about how digital audio is transmitted and audiophile concerns around jitter and noise. The motivation for the presentation came from people asking me about it, but also this video from Darko Audio, a YouTuber that covers audio. And the meat of the topic's actually after the introduction, but the introduction starts with him holding up these two bottles of water, saying that it's silly to ask for measurements of those when he could just open the bottle and taste them. And therefore, what he's about to present, which I'll talk about in a second, should not trigger anybody asking for measurements. And he goes on and says, you know, it would be very silly for somebody to go and demand that measurements be provided for bottles of water, and proceeds to taste them. And I think he naturally says that fancier water is better than the supermarket water. It's a mistake in what he's claiming, in that we don't ask for measurements. We'd love to see tasting and listening tests. In his case, all he's got to do is taste the two bottles of water blind, not knowing which is which, and then telling us which one's better. We love that kind of subjective control testing, far more than measurements. I don't even know what to do with measurements of water, but I do know that a lot of research is done in food, and tasting are done frequently blind. There are major cooking shows where the tasting is done blind. So I think his analogy is quite misplaced. Go ahead and have somebody else pour each bottle of water into two identical glasses, and let's have him test that multiple times, and then we can tell that his opinion is not biased towards price and looks and branding and so forth. And the meat of this presentation, as I said, comes later, in that this is a review of this streamer. I forget what the brand is at the bottom. It's a few $1,000 digital audio streamer, meaning that it can pull local content from your network or from the cloud, and then feeds it to a DAC, and then you can listen to it. And he's got a stack of them in here. As you can see, it's the largest one that I think Inuit was the one that it was testing down here. I think this is not a Sonos, who's their competitor? It'll come to me. And he goes up, this is Sonos over here, and then he's got an Allo one over here, and then some other embedded one. And sadly and naturally, he says the biggest and most expensive one sounds the best, and then, you know, progressively as the thing gets smaller and cheaper, the sound degrades. And then he confesses very quickly that, you know, this is incredulous, you know, to say that, you know, these digital sources have different sounds when the source of the content is identical. And he then goes on to explain that what is actually transmitted as digital audio is actually analog, and therefore is got all the problems of analog, and specifically has jitter in there. So, and he goes and you know, he's got a fancy production crew, and they overlay graphics and say, well, this is what you think a digital audio looks like, but in reality it doesn't look like this. And he's very correct about that. I'm going to talk about this in a second. So is digital audio transmission analog? The quick answer is absolutely yes. And it doesn't have to be digital audio. It can be digital anything. Inside your computer, there are tons of data streams that are running around, and the waveform can indeed be distorted. But what distinguishes digital transmission from analog is that we actually don't care about the small or even medium level changes in the signal itself. We set a threshold. If you look at the waveform on the right, we set a threshold in here. We said, look, anything above this threshold is a 1. Anything below this threshold is a 0. So I don't care that the waveform has been distorted over here. I'm easily able to extract a 1 and a 0, and 1's over here. And indeed, these signals can degrade very close to this line, and all is well. Now, once it gets really, really bad, and we flatline on the threshold, then hell breaks loose. But until that point, you know, the beauty of digital is that it can take an analog concept, with variations and convert it into something that's got exceptional noise immunity. And this is what makes it powerful. And the fact that we can ignore noise and variation completely sort of counters to what he's assuming and what he's talking about. So just because something is analog doesn't mean that it's bad. Yes, if we treated this as an analog voltage with all these variations, that would be bad. That's why analog has noise in it. But when we treat this digital, that is not the case at all. So at a fundamental level, there's a truism in what he's saying, but he's completely bastardizing this into something that he's not. Now, I could stop here and say that he's completely wrong, and I can get 100 digital engineers that sit next to me and just laugh at what he's presented. But I want to be fair. There are issues in here that go beyond the superficial treatment and dismissal. So let's go into that. Now, this pretty graph that I showed you, it only happens if, let's say I've got digital audio over very short distances. Instead of short distance, let's say I have a broadcast studio, broadcast studio, and I've got signals that are being transmitted between rooms and even buildings. Now we're talking hundreds of feet, and across hundreds of feet, these voltages come down in value. We get losses, we get filtering, these edges become less sharp, and indeed, damage can be done, and very seriously, to this waveform, to a point where it doesn't transmit digital data. And good news is that when that happens, the impact is catastrophic. In analog, if you keep increasing noise, it just gets noisier, noisier, noisier. Digital doesn't work like that. It has this cliff where the transmission is perfect to all of a sudden we can't capture something, and it could be 1 bit or it could be 1,000 bit in sequence that get corrupted. And when that happens, it's very catastrophic. In case of video, all of a sudden you see pixels that are gone and corrupted. You probably have seen this, especially if you have an antenna for digital video, TV standards. And for audio, most people assume they know what this sounds like, but they don't. And I've produced some samples of data loss over USB for that's transmitting audio, and I can assure you the sound degrades substantially. There's glitches, there's buzzing, there's pops, there's discontinuity. It is not at all the subtle thing where micro details change and the timing is changed, bass is a little softer. The data transmission has no notion of what that data looks like or what it is for. It's just a bit. And if you obliterate one or more bits, the data samples can vary sharply from one another. And that's what causes the ticks and pops and glitches. There's no such thing as a subtle degradation. Now, to make that data loss happen over USB, I had to create a 30-foot cable with 15-foot extensions of very, very thin USB cable with a lousy transmitter and receiver to cause it to have data loss. And in a good connection, actually, still couldn't get it to fail. And indeed, if you have a DAC that's hooked up or that's over SPDIF, coax, or USB, and is any reasonably short length of cabling, there is no data loss whatsoever. Just put that out of your vocabulary. Data loss can happen if you exceed the standards, and that means going many, many meters. So if you're going from one room to another room or upstairs to downstairs, yes, you can get data loss. But in any kind of stereo setup where you got a stereo system sitting someplace and you got your streamer here, and next to it there's a DAC that's 5 or 6 or 8 or 10 feet of cabling, it absolutely will not have any data errors. So assume 100% that there's no data errors. And if there is, know there's glitches and pops, and it's not some subtle staging or microdynamics or any other silly subjectivist commentary. Now, so far, I've only covered one aspect of digital audio, which is what the data samples are. He says, this is the PCM value of this, and the DAC will take that PCM value and convert it to an analog value, and it just follows whatever the digital stream is. But we also need to tell the DAC how fast the bits are coming, what is basically the effective sample rate of the data is, because we can have 44.1, 48, 96, and what have you. And the DAC needs to know that to be able to play it at the right timing. If it plays at the wrong timing, that can generate distortion. The most classic links that we have is coax and toslink. Both of them are called SPDIF, and then there's a AES EBU professional standard that's a balanced. And whenever you're using these connections, key thing to understand technically is that the host is a master. So if it's a streamer or it's a CD player or a computer that's playing, the host is telling the DAC, I'm going to send you the bit stream, and you better follow the bit streams and only output your samples whenever I give them to you. You might think, well, I'm playing 44.1. Can I just tell the DAC that it should play at 44.1? Answer is no. That's a nominal rate for it to display on its display, but the DAC is not allowed on its own to assume there's a fixed data rate. The host can actually change this by up to 5%. It can speed up and slow down even as displaying. And the DAC needs to stay in sync with it. This is called a master-slave kind of relationship, and the DAC is the slave. This is a very poor architecture. It was done for simplicity. And the problem with this scheme is that the DAC has to extract the timing of how fast the bits are coming at it and convert that to a sample rate internally. And unfortunately, with coax or any of these links, there's only two wires going there, a shield and a center data pin. There isn't a separate clock pin that says, hey, here's the sample rate that's coming at you, and just take this. The data itself has pulses, and these pulses need to be grabbed, and the distance between the pulses is what tells the DAC what the sample rate is. And the second thing that can happen is that there can be noise on this line, and that noise can actually be coupled from the host all the way out to the target. Toslink, being an optical link, helps a lot with this. Oftentimes people have ground loops, and you go when they have a coax connection or USB connection, and they switch to Toslink, and that goes away. So this can be a problem, and so the architecture here is limited, and it can have problems. So let's look at this thing with real detail and instrumentation. I took my audio precision analyzer, which has both a SPDIF output and input, and I had it generate this SPDIF signal, and then I took that and hooked it up to my oscilloscope, Tektronix oscilloscope, and had it display what is called an I pattern. So if you follow my cursor, so every bit sort of looks like this. Is basically negative, meaning it's a 0, and then it gradually goes up, and then it stays constant here, then it comes down. So you're seeing one bit. What is overlaid on it is another bit that has arrived and is out of cycle with it. This is a digital scope, so it's able to catch these things. And if you let it run often enough, where a lot of bits get overlaid on top of each other, you get what is called an eye pattern. It's called an eye pattern because these things look like two eyes if you look at it left and right eyes. And engineers talk about a clear eye, in that if this area in the middle is very clear and very wide, the receiver has no trouble extracting the data from this link. And indeed, that's the case in here. Even though I have a cable that's 3 to 5 feet between the audio precision and Tektronix scope, we can see the eye patterns is extremely clear. But we also see that, as Darko has said, is that this is not digital, the waveform. The waveform actually has a slope to it and gradually goes up to 1. And the DAC actually grabs this zero crossing over here as the timing point of view. So it says, okay, start a clock here. Okay, the next one came over here. And these 2 points are now the distance between them measured in time is now your sample or bit rate that's coming at the DAC. If you take this waveform now and jiggle it left and right, what we call jitter, or make it noisy where the edges are fluttering over here, this timing measurement can get changed as well. It can have random errors in here, or it can have deterministic. So let's say the waveform jumps once a second left and right, well, that'll also transmit to the DAC. Now, good news is that the DACs have been designed to actually work in a far more hostile environment, all the way up to what the spec requires. So you could have 50, 100 feet of coax cable. So they have an internal flywheel mechanism. If you know how turntables use the momentum of the platter to get a steady speed, they have their own waveform called PLL, or phase lock loop. And the phase lock loop, it basically measures these timing and generates an internal clock that's immune to high frequency changes. Low frequency can still get through, but high frequency one, it just filters them out and doesn't care. So if there's very high frequency noise in here, let's say from your cell phone or Wi-Fi or AM station, FM station, everything, it happily filters all that and gets a clean one. And we can see in here the waveform is very clean anyway. This is an actual waveform. This is not a made-up thing. And the scope is receiving and displaying it. And we can see that we have no trouble over here. And these edges in here are quite precise. So we don't need that, but if we do need it, the mechanisms inside your DAC. And that's why when you go change one digital cable to another digital cable, you don't notice anything, because of all the filtering is there and the fidelity of the signal is already quite high. USB audio started off using a similar kind of mechanism. The people designed the USB audio initially, and the audio devices worked the same way, in that the PC was the master and the DAC was the slave. That actually caused worse jitter than SPDIF, because it's a computer, and the computer just doesn't care if that timing is so precise as far as the USB packets coming in. But after a few years of USB audio being out there, some clever folks came up with a mechanism to use an asynchronous mode of USB, where the USB is still actually trying to transmit real-time audio stream, but the DAC picks its own clock. So this time he says, hey, I'm playing 44.1, and I'm going to tell the host, if it's 5% faster, I'm going to say, hey, slow down, slow down, slow down, till it slows down to 44.1. And if it's going too slow, I can actually tell it to speed up. So it's like you being in charge of a autopilot. You're basically accelerating, decelerating, cruise control in your car. And that's what this is, a mechanism where because USB products are smart, they have memory, and they can have a cushion against the host not being in sync with it, is able to basically eliminate any dependency whatsoever on a digital clock in a USB. So USB is also serial link. It does have a separate clock, but its clock could also have all the noise issues that I've talked about. But that clock on USB is only used to extract the data. Once the data is extracted, it's never used for timing. The timing, the DAC is the master, and you can have a very high precision, high quality clock that's right next to the DAC chip. Doesn't care at all about like SPDIF trying to measure those corners and arrive at good timing. Okay, so in case of USB, we don't worry about data errors, and we don't worry about jitter over USB bus. It simply is not something that's in the vocabulary that we have. So do we say that the bits are bits? It's a common objectivist thing to say, and laugh at anybody who says, digital audio can degrade performance. The answer is no. You can't say that, because I've talked already about noise and jitter. And let's talk a little bit more about noise. A USB cable has data and clock, but it also has power, and it also has a ground. Some DACs run on that USB power. I had a Shet Modi 2 that any noise on a 5-volt supply would translate into a hideous jitter on its analog output. And you could take that DAC and plug it into 5 different computers, you get 5 different measurements. And fortunately, that's an example of something that just shouldn't have ever gotten out. And even at that time, there were a ton of other DACs that didn't have this problem. And today, the quality of USB receivers on anything I test and recommend is just superb on this front. Although occasionally I still run into this in some AVRs. I see this thing, some smart amplifiers. I've found that their USB receivers are not robust, and that can pick up noise through either ground or voltage. Excuse me. one of the common symptoms that a lot of people report, for example, is that with an internal DAC to a computer or even a crappy DAC externally, when their computer gets busy, they can actually hear the activity, especially when the GPU, the graphics processor inside a computer, starts to get going. They can hear, different kinds of noises all the way through their audio device. So that proves that bits are not bits. Because remember, the data hasn't changed, so that from that point of view is the same. But because we have an electrical link, that electrical link ultimately can transmit stuff. You can have a galvanic isolator that you can buy either separately or one that's in some DACs that really provides complete isolation between the two. Fortunately, if you get a good DAC, 99.99% of the time, it's not a problem. And if you use balanced audio output, as I always recommend, that actually becomes quite immune to this problem. It's only mainly an issue when you have RCA connections on your DAC. Okay, now does this mean we don't get jitter and noise? Actually, we get plenty of it, and I measure it all the time. The main source of jitter and noise isn't the link or the host behind it. It's actually internally generated. A DAC is a mixed signal device. It has both digital and analog subsystems, and a lot of times the noise inside its own digital section can bleed into the analog, or you could have lousy power supply that has noise on it. All of that gets translated to an analog output of the DAC. Reason is that audio DACs have extremely high resolution, the bit depth. Even a crappy one, say 16-bit CD audio, we can go all the way up 24 bits. So even slightless, movement in those samples generates error. So from that point of view, it requires a very, very clean implementation. Fortunately, we get that in a lot of devices. Now, what I've highlighted in here is that to know that if we have a problem here, we measure. We can measure jitter, we can measure noise, all the things that Darko says, well, we can't measure, we should measure. It's like, no, if you're going to talk about something technical being a problem and you name it as jitter, well, we have tools that let us measure jitter. So here's an example of a topping DM7 and a channel DAC that I measured, and this graph is just from the review itself. And I feed a special signal to it. It's called the J-test. We can see that the noise floor down here, that's in the analysis, I can bring this noise floor down and able to even resolve these spikes in here. This is a valid set of bits. That's a single bit toggling at the limits of 24 bits. So we're able to actually correctly see the sequence of bits in here being resolved. And if you look at the spectrum in here, just absolutely clean. All we see is just randomness of noise at extremely low levels. So it's an example of a case where this is running from my computer, which is a noisy source and a noisy streamer, and it's wailing with 16 cores in it and GPU and everything else, yet this DAC absolutely does not care, and it's producing exceptionally clean signal, resolving it down to 24 bits of resolution. But it's not always that way. As I mentioned, these things can degrade. And here's an Onkyo TX RZ50 that I tested, I think, a year ago. And we can, actually a few months ago, 212. And we see that not only does it have all these spikes, this is identical measurement. So it should be just like the other one with noise down here and just a few bits down here. But instead we get this regular pattern. This regular pattern is actually part of the J-test signal, and is bleeding from the digital section that's receiving that data into the analog section. So remember, all these measurements are actually measuring what comes out of the DAC. I'm not actually measuring its clock to see how accurate it is. I don't care. It's a black box. I just say, give me your waveform, and the waveform should only have this one spike in it at 12 kilohertz. Anything else is unacceptable. So all of a sudden, we see an excessive pattern over here over coax. Over HDMI is much cleaner, but its noise floor is still way up here, much worse than what I just showed you. But you still notice this comment in here. As bad as this is, with the eye being insulted that there's all this in here compared to the other DAC, I look at these measurements and I say, look, the threshold of hearing is around -115. So almost all of these things are below threshold of hearing. The few of them over here are above threshold of hearing, but they're right next to a very strong 12 kilohertz tone, and therefore masking will make sure that you don't hear that. And on top of that, real content doesn't have full amplitude 12 kilohertz anyway, usually. So as bad as this is, you're not going to hear jitter this AVR. You know, technically it's poorly engineered. It shouldn't have this, but the fact that it does is still not a bothersome thing. Now, there's an automatic assumption that the better the story and the higher the price and the fancier the brand, the cleaner these things must be. It's not so. I've tested a lot of products. Indeed, unfortunately, many high-end products have inverted performance where the price goes up, but performance also goes down. And how do we know that? We measure it. So this is a $2,500 DAC. This is an Audio GD Master 7 Chinese DAC that is revered. Used to be so. It's a massive box with tons of over-designed circuits in there. But look at this jitter performance. USB's down here is still not as clean as what I showed you in topping. It does have some jitter components, but again, they're at minus 130 dB or so. When I switch to coax and toslink, all of a sudden the problem gets far worse. Remember, now it has to go extract the clock itself, and when he's trying to do that, it just is doing a very poor job in here. And is it going to be audible? No, this threshold of hearing is way up here, and just shows poor engineering. It's like, if you can have clean jitter and noise, why not get that and put up with this thing? And now you wouldn't pay $2,500 and still got worse performance. This is a recent example that I tested, this name unity atom. This is coax input. And look at the noise floor up here. It's way elevated in here, which means it's got random noise that can cause jitter. It's one of the things. But one of the other things it does is that it masks all the jitter components below this. So these, you know, if the noise floor was down here, we would see a very horrible looking picture with all these spikes being jitter components over here. And right now they look like they're small, but in reality, they're way above a good noise floor of another system. Clearly, this is not something that you want to be proud of. You paid a lot of money for this DAC. I forget how much it is. It's thousands of dollars, and you know, look at the noise floor that you get. So more money didn't get you less noise and less jitter. Another example, $7,500 SACD player, CD SACD player from Rand's SA10, and look at these pronounced spikes in here. These are all digital activities inside the unit that are bleeding into the clock circuits or reference voltage of the DAC, resulting in this deterministic spikes coming out here. Again, I'm always fair. I do a psychoacoustics analysis real quick, and I say, well, threshold of hearing is at minus 115, so no, this is not going to be audible. But boy, you know, you pay $7,500, big, heavy CD player, but, you know, you get in far worse performance than my computer. This is my computer for driving a DAC that's just a few $100s, and it's 8-channel DAC, and you get this clean, and then you go get a, you know, $7,500 transport, thinking, oh my God, it's going to be so much better digital stream that it outputs. It's like, no, it's not very clean. Let's talk about a streamer, back to the, you know, what Darko talked about. I've measured the digital stream coming out of a lot of streamers that have SPDIF output. And I tell you, it's just going to become boring because the amount of jitter they have on those links on a short length of cable, it is so small as to not matter. And any little bit that it does have, the DAC will filter it anyway. I can show jitter down to 1 or 2 picoseconds, and I've shown that, but it's like 1 or 2 picoseconds. I mean, it's just not something that's in our vocabulary as far as impact audibly. Now, let's look at an example of a streamer that was way on top that he was showing. And this streamer, not only is it a streamer, it's built on Raspberry Pi, a single board computer, but also has DAC built in, and the whole thing costs $210, $209. Look at its performance over here. Look how clean it is. It's not as perfect as what I just showed you in the topping standalone DAC. We have, you know, a few spikes in here. It could be jitter, spurious things, but their levels are minus 140 dB in here. So absolutely, utterly inaudible and not a concern at all. And if a $200 DAC and N streamer combo can produce this, why would we worry to, you know, say, well, is there something that's cleaner than this? I've already been explaining this to you. Every time I make this jitter measurement, I do a psychoacoustic analysis, as I've been showing you. And, maybe once or twice I've seen something that made me think, oh, wait, that could be audible. In general, it just shows, poor engineering. I said, look, you could have designed this product without this and cost nothing more. I mean, basically, it's just poor engineering, design skills, hygiene, that causes that lack of isolation and poor clock extraction. There's no reason to have jitter. This has been, people have had 30, 40 years of experience dealing with digital audio jitter on this thing. So even if we do have jitter then, it means that saying that jitter equals bad sound is not valid because, across almost 400 devices that I've tested, maybe one or two of them have had bad jitter. The other ones, no matter how bad they are, they haven't risen up to the level of audibility, let alone be something that's nasty. But we only know that because we measure. So if you go by random $5,000 streamer, just like that Moran's transport, it may actually be worse anyway. So this lay assumption that I paid more and it's more expensive and it's a bigger box, therefore must be cleaner, is wrong, and certainly wrong to just run around and say, oh, our differences in sound on this thing. Okay, so translating this into streamers, basically, if the streamer is outputting digital stream and it's got a USB connection or even SPDIF connection, and you're getting a good DAC that I recommend, which goes down to $100, it's just a non-issue at all. And performance is the same regardless of the noise of the source. A lot of people say, oh, a computer's noisy, therefore a dedicated streamer must sound better. No. Every measurement that I make, I actually use my computer as a streamer when I test streamers, and there are streamers I've measured that have signage of 120 dB. They're as squeaky clean, as low noise as you can possibly get them. So it is true that sources can be noisier than others, but it is not true that you can just, wet thumb in the air and say, oh, this is noisier than the other one, therefore must be worse or better, as Darko was doing. There's zero legitimate reasoning behind that. We can measure it, and across all these devices I've measured, what he's doing is just totally, totally incorrect. Okay, so where are we? It's just not a concern. I get this all the time. What streamer should I buy? I said, buy the one that has the features and the price and the support that you want. That's what I do. It just makes no difference. My main system, I built a silent Windows PC, and that runs the room server for me, and that is my streamer device. Would I do it again? I don't know. I don't like the fact that Windows Update constantly reboots it, and sometimes Room doesn't start, and I gotta go manually restart it. And so from that point of view, it's not good. Know that every other streamer you buy that is not a Windows or a Mac PC is going to run an operating system called Linux. Because of all the networking and other features you need a full-blown OS. Therefore, it's a computer. Usually, it's a multi-core CPU. Yes, it's not as high performance as a computer is, but it's not a noise-free little, custom circuit. It's a full-blown computer that's in there, and you have challenges in that you may not get updates if that company goes out of business. How are you going to get it to work or support new features in the future? Nice thing about a PC or a Mac is that it's an open platform, and forever you're in charge of that. The downside is the manageability of it. So you got to decide, what works for you. But that is the important thing. The next important thing is to get a DAC that I recommend, and I've recommended, I don't know, probably 100 DACs, and out of them, 50 of them are just amazing performance, state of the art. For good measure, use a balanced XLR connection. If you can build a DAC and a preamp and amplifier that all balanced, you save yourself a lot of grief with ground noise and ground loops on that. And you do that, you'll be 1 in a million that you're still going to get noise and what have you. Jitter is just not a concern in any of those. Now, I've talked about a lot of measurements, but I started the whole presentation on subjective testing. And I absolutely love to see subjective testing from any reviewer, but subjective testing needs to be blind. It can't be based on price and size and who gave you a freebie unit the next day, the previous day, and what have you. If you think the sound is so easily distinguishable from one to the other, just do the listen test blind. The digital levels likely are the same. So just have someone do an A/B test for you, repeat it a dozen times, and let's see if you get 8 or 10 times out of 12 that you guess correctly which one's which. Then it's fantastic. We'll chuck all these measurements aside and we'll go by that. Shoot a video of that, document the protocol, how you did that, that's great. But if you're gonna do a cited test as Darko's done, it's just as worthless as a fortune cookie at a Chinese restaurant. You know, it just means nothing. He's so biased by classic folklore out there. And I can't blame him personally because so many people are biased to think if you pay more, you get more. That's how real life works. You know, you buy a $100,000 car, it's comfortable and faster than a used $5,000 car. But just know that when it comes to audio, unfortunately, that equation has been thrown out a long time ago. Companies are happy to sell you stuff that's super expensive because so much of it went into the channel that distributes it, the machinery, all this other stuff that is not performance related. Okay, hopefully you learned something out of this presentation and you're more educated, both when you're talking to objectivists and subjectivists, because there are people mistaken about these concepts on both sides of the equation. Okay, see you in a future video. Bye-bye.